From the molecular formula, we calculate that the molecule contains one unsaturation. Two signals are present, indicating two sets of equivalent hydrogens in the molecule. There are additional peaks in the spectrum which do not belong to the sample. The peak at 0 parts per million is the signal of the internal standard, TMS. The peak at 7.27 parts per million is the signal of chloroform, a common NMR solvent. Other small peaks in the spectrum are caused by traces of water and by impurities. In integration mode, determine the integral value of a signal in the spectrum by clicking to the left, then to the right of it. The integral value will vary depending on where you select the boundaries. They should not be too close to cut into the peak, but should exclude impurities. The integral values for the two signals are 1 and 1.48. Adjusted to half integers, the integral values are 1 and 1.5, and the overall integral value is 2.5. Since there are 10 hydrogens per molecule, one integral unit equals 4 hydrogens. The first signal represents 4 hydrogens, and the second signal represents 6 hydrogens. In expansion mode, clicking on a point in the spectrum will enlarge a region 0.2 parts per million wide. In the expanded area, use the cursor to measure frequencies by clicking on the peaks and noting their respective values in parts per million. The chemical shift of a multiplet is the frequency at its center. The first signal has a chemical shift of 2.43 parts per million, which falls into the region for aliphatic protons with a weak electron withdrawing substituent. The second signal has a chemical shift of 1.06, which falls into the region for unsubstituted aliphatic protons. Since it is around 1, this signal most likely represents a methyl group. The first signal is a simple quartet, which means that it is coupled to a set of 3 equivalent protons. The coupling constant, or J value, is the distance between any two peaks in Hertz. In expansion mode, click on one peak and note the frequency value in Hertz. Click on another peak and note the frequency value for that peak. Subtract the two values to obtain the coupling constant between the two peaks. .4 Hertz is a medium-sized J value, as expected for adjacent aliphatic hydrogens. The second signal is a triplet, which means that it is coupled to a set of 2 equivalent hydrogens. The coupling constant is the same as for the first signal. Therefore, the two sets of hydrogens are coupled to one another. A triplet and a quartet with the same coupling constant, at the upfield end of the spectrum, are the signature of an ethyl group. Since signal 1 and 2 represent 4 and 6 protons respectively, there have to be 2 chemically identical ethyl groups per molecule. This accounts for all the hydrogens and 4 of the 5 carbons in the molecule. The chemical shift of the methylene protons reveals that they are adjacent to a weak electron withdrawing group, such as a carbonyl group. A carbonyl group accounts for the remaining carbon and oxygen, as well as the unsaturation in the molecule. The compound is 3-pentanone.